Okay, so let's go back to some of what we have already seen. Now we know that near the band edge, I can use this parabolic approximation. We know that near the conduction band edge. So conduction band edge is say EC naught, and I can write the energy as EC naught plus h square k square by 2m. Right, m is the effective mass. We have seen all of that. K is the wave vector. Now in the semi-classical picture, we know that electron is going to behave like a wave packet. K will be the center point, because it can have several k values. So k basically here denotes the center value of that. Okay, so this is the parabolic approximation I was talking about near the EC or the EV. And in the semi-classical picture, we have a wave packet and it will have a crystal momentum, h bar k. Yes? It does not have a real momentum. I mean, it has a momentum, but h bar k is not the actual momentum. H bar k is the crystal momentum. We have seen that. You know, h bar k is not the eigenvalue of the momentum operator. We saw that. Yeah. But this still helps us to explain, the semi-classical picture of the wave packet. So we'll go with this. So Pc is equals to h bar k. We know that. So it's like a particle of the crystal momentum. And what we can do, now we can divide this energy in two parts. So this is your EC naught, and then h square k square by 2m is another term. And this E is the total energy. Correct? Now, h square k square, h bar square k square is Pc square. Pc square by 2m. What is P square by 2m? Momentum square by 2m. What is that energy? Kinetic energy. So this part is kind of a kinetic energy. And this is the total energy. So what should be the rest? It's simply the electrostatics. There are no, say, friction forces as of now. So you have the kinetic energy. What other energy can be there? Potential energy. So rest of the energy will be the potential energy. So this EC naught, the band edge, that represents the potential energy level. Correct? Okay. Now this expression, of course, we did not apply any electric field. We assume that the electric field was 0. Yes? If I now do apply the electric field, what will happen? Electric field will generate its potential. Whenever you apply some voltage or some electric field, it gives you some potential energy. So if I have an electron which is moving inside a potential, which is moving inside an electric field, it will experience a potential. Yes? Correct? What is that potential energy? Say, if V is the potential energy, value of the potential, then what will be the, say, potential energy of electron? If my potential at any point is, say, V, what will be the potential energy of electron at that point? Charge times potential, correct? Minus E times V, correct? Or minus Q times V. So when I apply an electric field, one potential energy is already coming from the crystal, which is EC naught. On top of that, I apply some extra potential that gives electron an extra potential energy. What will be that extra potential energy? Minus Q times V, or minus E times V. So when I do have an electric field, the total energy becomes EC naught plus the potential energy coming from the electric field, which is minus of Q times V in case of electrons. It will be plus Q times V in case of hole. It's a positively charged particle, plus the kinetic energy. Now this whole thing, we combine it and we write it as EC as a function of X. Okay? EC naught is constant, it's a number. It does not vary with X, but this potential can vary with X. Say potential is, say, linearly varying with X or some non-linearly varying with X. It can be a function of X. True? Yes? In fact, if I have a constant potential, I can't have an electric field. So because it's a gradient, right? Minus dV by dx is equals to electric field. So potential will vary. So because it will vary, so this term is going to vary. So my potential energy is going to change from point to point. So that whole potential energy, the total potential energy, now I'm calling that as ECX. And this is what is your conduction band edge, the final conduction band edge. When, you might have seen that your EC is varying with X. So what is that EC? That is not EC naught, that is EC naught plus the potential energy coming from the external field. So it is the combined EC. Okay. So this is the total potential energy. Now let's look at energy band diagram. So we have seen EK diagram. So EK diagram represents the energy as a function of K. Energy band diagram is a little different. So energy band diagram will represent the potential energy of the electron or the hole as a function of X. Okay. So say I have an electric field. So of course there will be a force acting on the electron. And if I have a force acting on the electron, what will happen? Its momentum is going to change, right? So what is the momentum? Momentum is basically K vector, H bar K. So momentum will change. Why will the momentum change? Force changes the momentum, Newton's second law, right? dP by dt is equals to force. By the definition, the force is equals to rate of change of momentum. So electric field is going to apply the force. K will evolve with time. How does it evolve? Force is equals to dPc by dt, and Pc is h bar k, so h bar into dk by dt. We have seen this so many times now. So force is equals to minus of q times the electric field, electrostatic force, and we know that electric field is further minus of dv by dx, del v by del x, right? So that minus minus has become plus here, and del v by del x, can I relate it to the conduction band edge? Yes. So EC is equals to EC naught minus of Q times V. Correct? So if my potential is varying, so is my EC. So you can, it will become minus of del EC by del X. You can check. Right? Q times into del V by del X will give you minus of del EC by del X. But what is the significance of all of this? What's the significance? It says that whenever my conduction band edge is a function of X, so if it is varying, it is going to definitely change my momentum as a function of time. Right? If it is changing the momentum, basically it's changing the K vector, or you can say the kinetic energy. Okay? So if you keep moving in certain direction and your conduction band edge is varying with X, it is also changing the kinetic energy simultaneously. It has to. Okay. And there is a negative sign here. And you have a positive sign here. What does it mean? So whenever my potential energy is, say, decreasing with X, momentum vector is going to increase. There is a negative correspondence. If my potential energy is increasing, momentum vector will decrease. True? There is a negative here. So there is an inverse correspondence. So whenever my potential energy is going down, okay, EC is the potential energy. If it is going down, K is increasing, it means kinetic energy is increasing. If my potential energy is increasing, my kinetic energy will decrease. So that is in correspondence with the conservation of energy. The total energy will remain constant. So whenever you decrease the potential energy, kinetic energy will increase. You increase the potential energy, kinetic energy will decrease. Okay? Total energy will remain constant. Again, I'm not assuming that there are any other forces other than the electrostatic forces in my system. Only then this is valid. Electrostatic force itself is a conservative force. Conservative force means that it is not going to it is not going to change the energy, total energy of the system. It's going to conserve that. Okay. So this is there. Now we can show it in the form of a diagram, and that's what my energy band diagram is. Okay. Now look at this. So here I have my EC and it is decreasing with X. This is my total energies. When you start from here, you can make an EK diagram here. Okay, so this represents the minimum point of the EK diagram. We know that it is the band edge basically, right? And say the band edge is here, right? And corresponding to this band edge, say I have this much kinetic energy. Of course, because say my total energy is lying somewhere here. So this part is my potential energy, this part up to this part. So what should be the rest? Rest should be the kinetic energy. Correct. And if I have kinetic energy, I will definitely have a finite K. Okay. Now you keep moving in this direction. Say now I am here at Z equal to Z1. And now I draw the same EK diagram. What will happen? Because my potential energy has now gone down. So this edge is now lower. But my total energy has to still remain constant. So now larger portion of the kinetic energy is going to make up with the total energy. True? So kinetic energy will have a larger value now. You keep decreasing the potential energy more, kinetic energy will take up more of that portion. You get my point? Total energy is constant. You are reducing the potential energy, kinetic energy keeps increasing. And your, of course, the wave vector also keeps increasing. The magnitude of that. So this thing is energy band diagram. So I have drawn it only for the electron. If I draw it also for the hole, then it will make the complete energy band diagram. But it's the same concept. Okay. And one thing you can, just always remember that. So del EC by del X, whenever it is greater than 0, so that will imply that my electric field is positive. It is in the positive direction. Why? Because look at this. So you have minus Q zeta and minus. So minus will be plus. So zeta and del EC by del X, they have a positive. Positive here, positive here. So whenever my EC is say increasing, so del EC by del X will be positive. So that will mean that electric field is positive. If my del EC by del X is negative, electric field is negative. Or you can say that whenever I move in the direction of the electric field, my EC will increase. Whenever I move opposite to the direction of electric field, my EC will decrease. Okay, remember this thing. It will be very useful. Okay, now let's complete our energy band diagram. So we have seen that the total energy, if I plot that as a function of X, so that is going to give me the energy band diagram, but it can be the conduction band edge or the valence band edge. Both can be there. So typically we have seen that EC and EV, we draw them as the flat, as a function of X, right? But if I apply the electric field, so they will not remain the flat basically, okay, because they will have some kind of a gradient. Okay, so this is the electron energy. If I move up, where is the whole energy? If instead of say electron energy, I want to draw it on the y-axis, if I want to draw the whole energy, where will be that? How does the whole energy increase? In this direction or in this direction? Electron energy increases in this direction, I know that. Whenever I'm going from the conduction band to the, valence band to the conduction band, my electrons are getting excited. They have a higher energy. What about the holes? A hole which is here versus a hole which is here, which one will have a larger energy? Because hole is positively charged, right? So the potential energy will have exactly the opposite sign. True? If it is minus of Q times the potential for the electron, it will be plus into Q times the potential. So it will be exactly opposite. See, if I move in this direction, whole energy will decrease. If I move in the opposite direction, whole energy will increase. Right? So, whole energy increases like this. So, if I have a hole say here and if I have a hole say here, so this hole will be more energetic than this hole. Okay? And what is the distance between the edge and the actual location? That is your kinetic energy. So this, say I have an electron here, so this is the kinetic energy. If I have a hole like this, so this is the kinetic energy. If I am farther from, say, the valence band, my kinetic energy will be larger. Okay. Now, how do we measure this EC and EV? I mean, of course, experimentally you can, there will be some measurement method, but what is the value of EC and EV? We never talk about the value of EC is equals to this, EV equal to this. Can I do that? Okay, can I write the potential energy equal to this? I have a formula for kinetic energy. We know that it is P square by 2m. Do I have the same formula for the potential energy? Of course I do. Force is equals to minus of del EC by del x. I do have that. But if I do it, say F is equals to minus of del EC by del x, right? I will have to integrate this equation for sure. So EC will be equal to what? Minus of F dx integration. Okay. And when you integrate, what will happen? You will have some function of x plus some integration constant. How will you calculate that integration constant? Boundary condition. True. But how do you determine the boundary condition? You will have to arbitrarily assign some value of the potential energy at a particular x. So unless you have a reference for the case of potential energy, you can't evaluate the potential energy. Potential energy is always with respect to some reference. When I say my mass has an energy of mg into height, mass into g into height, then that is with respect to the reference ground. It is with respect to ground. So at the ground you have assumed that the potential energy is 0. Then the energy of the mass is mgh. Okay, it is not that the absolutely this energy is mgh. No, that's nonsense. It is always the difference of this energy and the reference energy that is there in the potential energy. So you always need a reference. Reference can be any arbitrary energy level. Okay, it can be any energy level. E reference, I can assume that this is my reference energy level, or I can assume that EC itself is my energy reference, or EV itself is my energy reference, or Fermi level is the reference, anything. So what you will typically do at a particular location, you will assume that, yeah, this is my reference, and now I'm going to calculate all the energies with respect to the, say, energy at this point. Say in a MOSFET, you have source and drain. People who know the MOSFET, right? You have source, you have drain. So drain you typically apply high potential, source is usually grounded. Usually we assume that the Fermi level at the source, that is my reference energy. And all the energies I'm going to calculate with respect to that. Okay, sometimes it will be, say, you have a MOSFET and you have this substrate and you have grounded the substrate. So you can also have the potential energy, kinetic energy with respect to this, say, the Fermi level in the substrate. Not necessarily Fermi level, you can pick, say, the conduction band in the substrate. Okay, so typically the points which are far away from the main activity of the device, usually they are neutral regions. They are for convenience taken as the reference points. Now it is not that you have to take only the neutral regions as the reference energy. You can take any. Okay, but it's just for the convenience. Okay, so there will be some reference energy level. Okay, this can be any energy at any particular point. Okay, so this is when I don't have an electric field because the bands are flat. What if I do have, say, a potential because of an external field? Same, I apply an electric field, and that gives me this potential profile. When I say potential profile, it means I am talking about the potential as a function of the distance, x, y, or z, whatever. So V as a function of x. Say it is like this. Now it is flat here, increases and again flat. And this is arbitrary to within a constant. Of course, they say this is the energy level. This is this reference energy or reference potential. It's the same thing. How will my band diagram look like? Let's start with the conduction band edge. Conduction band edge is equals to EC naught minus of Q times V. True? So EC naught minus of Q times V, plus you can also add some constant. Doesn't matter, because it is going to be with respect to some arbitrary energy reference. So even if I add some constant, doesn't matter. Okay. So this constant will be determined. It can be 0, it can be non-zero. It depends where is your energy reference. So EC naught minus QV plus constant. Okay, now I know that my conduction band, the valence band edge is going to be EC minus EG. True? EG is the band gap, that is a known energy. Right? So if I know the variation of EC as a function of x, EG is constant, I also know the variation of EV. True? Yeah, this is a function of x, this is constant, so EV becomes a function of x. And it will vary in exactly the same manner as EC. It is just that it will always be EG smaller than EC. Correct? And EI is the intrinsic energy level, which is roughly EC plus EV by 2. So we also plot this because this is useful in devices. Say I have a homogeneous material in which my EG is constant, it does not change with x. Sometimes the band gap can also change with x. Okay, it can happen, but for a homogeneous material, if you don't have a heterogeneous material means, say you have 2-3 materials stacked together, right? So in that case, every material will have its own band gap. Then EG will become a function of x. I'm talking about, say, a simple silicon bar, homogeneous material. EG does not change with x. So for that, what will happen? It will be simply some inverted shape of this, correct? Because EC is equals to EC naught minus of Q times V. So if my V is increasing, the potential energy has to decrease in the same manner. And this is my conduction band edge. So where will be my valence band edge? Exactly EG times smaller. So it will be exactly parallel to this EC. And where is my EI? Exactly in the middle. I mean roughly in the middle, not exactly. Where is my Fermi level? Fermi level will be somewhere, okay, depending upon n type, p type, but it will be always a flat line, a constant line, if the total current in my system is 0. If I do have a current in my semiconductor, then EF will also vary. If I don't have a current, it's going to be constant. Plus some other things, if you do, throw some light on the semiconductor, EF will not be constant then. It will be a function of x. Okay. Normal cases, say equilibrium case, EF is going to be constant. We will prove that. So the next topic is scattering potential. So whatever picture we saw till now was an ideal picture. We saw that if you apply some potential, the potential energy will decrease, kinetic energy will increase, and it will increase forever. Keep decreasing the potential energy, kinetic energy keeps increasing. But in reality, that's not how the transport happens. So there are imperfections in the crystal. Whatever I told you, that is true if my crystal is perfectly periodic. Then my wave packet picture, evolution of the K, all of that is a good approximation in the semi-classical sense. But reality is very different. Your periodic potential coming from the crystal it is never perfect because crystal has some imperfections. Now, what kind of imperfections can be there? There can be some defect. Say some atom is missing from its place. So what will happen to the potential at that point? Potential will be deformed there. So say if you have some periodic potential and I remove one atom from its place, so what will happen to the periodic potential at that point? There will be some deformation. Yes. Say if I have, say, an ionized impurity and most of the atoms are silicon atom, but where I put my ionized impurity, say positively charged or negatively charged, donor or acceptor, what will that do? Now that is not exactly the same atom as the silicon. It will have a different potential and it has a positive charge. So it will create some deformation at that local point. Okay. And that becomes the scattering center. When do the scattering happen? Whenever I will have anything different from the perfect periodic potential, I will have scattering. Scattering means your electron is traveling like a wave packet. Okay, it has some group velocity. Now Vg is equals to d omega by dk. How do you calculate the group velocity? From the Ek diagram slope. Yes, 1 by h bar d by dk. So if my crystal is perfect, that will remain constant forever. The group velocity is not changing. Unless of course you apply the electric field, change it. But it is always given by the curvature. True. But when I have these imperfection, that becomes invalid. So your electron is moving with some group velocity and it encounters something different, it scatters. Okay? Say I don't have any defect, any impurity, nothing. No charge, nothing. But I have temperature. Instead of, say, at very low temperature, say 0 Kelvin, I am keeping my crystal at room temperature, 300 Kelvin. What will that do to my atoms? They will oscillate because of the thermal energy. That is also a perturbation. Okay, that is also a perturbation to this perfect periodic potential. That will also scatter the electron. So all of these imperfections are going to scatter the electron, hence the name scattering potential. And of course, if it is scattering my electron, what will that do to my conductivity? It will limit it. Okay, it will definitely limit it. If my, say, electron could have moved with some velocity and it is encountering some scattering, of course it's going to slow down the transport. So this is say the perfect periodic potential. Of course at the edges you don't have that perfect periodicity, but within most of the bulk of the semiconductor you have this perfect periodic potential. Then you define another quantity called scattering potential. So scattering potential is that extra imperfection which is coming because of the defect or some charge, some say dopant, right? So there can be some traps. Traps are, we'll talk about it. So there are some energy states which can be charged, or the temperature. So that will look like this. Arbitrarily the potential is going to be some zigzag. Okay, so most of it is flat, but at some point you see these imperfections. So it is not zero everywhere, and because of this there will be some scattering. If there will be scattering, so there will be scattering events. Okay, now even when my electric field is zero, I told you that there can still be scattering because of the temperature. Yes, I mean, I don't have an electric field. Electrons can still move because of the thermal energy. They have this energy and they collide with the lattice. Okay, or you can say they scatter. So that's how it looks like. So you have, say, an electron, going through this path. So this is, say, as a function of x, and then it encounters some scattering event, goes here, again, go like this, again a scattering event, come back. So this type of motion can be present when the electric field is 0. So in total you can say electron has not moved at all on average. Yes, it moved, but then it encountered some scattering, right, and then it came back. And statistically speaking, if you average out, you take the average of all the electrons, so you will see that there is no net current at any cross section. Electrons are randomly moving with some thermal velocity. They are moving, but 50% of the electrons are, say, on average moving in this direction, 50% are coming back. Okay, so at any cross section, net current is going to be 0. Okay, what happens in the energy band diagram then? So whatever we saw, what happens to that picture? We know that when we apply the electric field, of course my K vector evolves using this Newton's law, and we then drew these energy band diagrams. So potential energy is decreasing, and we assume that the kinetic energy should increase. Say I started here with 0 potential energy, and according to my picture, the perfect picture, if I come to this potential energy from A to B, the total energy is constant. So this much energy should come from the kinetic energy at point B. Correct? But this usually never happens. It never happens in reality. So before it reaches here, what happens? It encounters some scattering event. So it loses its energy. Okay, it comes near the conduction band edge. Whenever I'm near the conduction band edge, my kinetic energy is negligible. Okay, it is small. So it started from here, it accelerated, K vector increased a bit, but then it encountered the scattering and it lost that energy. Again it picked up, gained some energy, again lost it. Now this loss of energy, it can be in multiple steps. So I have drawn it vertically, but it could be like a stair. Okay, it could be a gradual decrease also. So instead of one scattering event, it can have multiple scattering events before it comes down to, say, the bottom of the conduction band. But it will have scattering events. It accelerates, encounters some scattering, goes down in energy, again picks up, again goes down. So that's how it moves. But it is moving, at least it is moving from here to here. Unlike this, where it wasn't moving at all. So on average, you can say that electrons is picking up energy, losing energy, picking up energy, losing energy, but it is moving in a particular direction. Okay, if it is electron, it is moving in the opposite direction of electric field. If it is hole, it will move in the direction of the electric field. So for the hole, you can say the same. Yes. So hole picks up the energy and then it loses the energy, picks up the energy, loses the energy. Whole energy is in this direction. So exactly the opposite. So there is a term called drift. Okay, drift of electron. So what is that drift? When you apply the electric field, electrons start to move in the opposite direction of electric field because the force acts in the opposite direction. It's a negatively charged particle, and for the hole, it acts in the direction of electric field. So electron will move in the opposite direction, hole will move in the direction of electric field. So that's how the motion will look like. But as soon as they start to move, they will encounter some scattering events. Now if I plot, say, my momentum h bar k as a function of distance, so how will it look like? It will look like this, as a function of not the distance, as a function of time. So h bar k, dk by dt, it is proportional to force. So if, say, my electric field is, I'm assuming, positive, so it will increase the k, then it encounters some scattering, suddenly my momentum decreases. Okay, it can also happen, it changes the direction also. So k can become negative. Okay, then again it picks up, again there is a scattering, and that scattering this time has made the momentum positive. So all of these scattering events can be there. And it is not necessarily linear always. Okay, so if my force is constant, only then it will be linear. dk by dt is equals to constant, some constant, so that will give you linear. Otherwise it won't be linear, it can be non-linear also. And if you plot the distance as a function of time, so overall you will see that yes, my momentum, momentum is basically roughly related to the velocity. Correct. So if my electron is moving in a particular direction, so the distance is increasing, and then suddenly it goes down, so distance starts to decrease. Okay. But again it picks up, right? So it keeps going like this. Comes down, again picks up. So overall you can say that electron has now reached at least some distance from 0 at this time. So this z is non-zero. So it has traveled. Yes, it goes, comes back, but it has traveled. So this is called drift. So all of your electrons are drifting in the electric field. They are not freely moving, but this distribution is kind of drifting. Right? It is just moving. Or drift is, that's why a better word. Okay. Move means it is moving like without any restrictions. Drift means yes, they move, they come back, but overall they are still drifting. So the movement will be something like this: goes, come back. Okay. If there is a drift, we can define a velocity called drift velocity. So drift velocity is basically the velocity if you apply an electric field on average with what velocity an electron is drifting. Okay, it is moving, coming back, moving, coming back. If I take average over all the electrons, this distribution is still moving with some velocity. So that is the drift velocity. So drift velocity, how do I define? How do I calculate? Again, let's start with our Newton's law, semiclassical relationship. I can replace this, so I can relate this k with my velocity, the group velocity. What is the group velocity? So group velocity is the v equal to 1 by h bar into dE by dk. Correct? Now, this is going to be simply, if I assume that I have a parabolic approximation, so this dE by dk will be equal to h bar k by m. You can check that. E is equals to some E naught plus h square k square by 2m. Calculate the dE by dk. That will be proportional to your h bar k. Obviously, h bar k by m. That's going to happen. And this is also, this is momentum divided by mass. So what is momentum divided by mass? This is the velocity. In a semi-classical sense. So v is equals to h bar k by m. So I can replace this k in terms of v. So that gives me dv by dt is equals to minus of q e by m. Correct? Now I can integrate this equation. Assume that say my say this electric field, say this is constant. I'm assuming that. So for that, what will happen? You integrate it from 0 to t, right? So this will give you v is equals to some v naught minus q tau into t by m, correct? Yes? Okay, so dv will be equal to minus of q into zeta by m into dt. You integrate, so from where? V naught to v, and from 0 to t, you get this equation. Assuming this is constant, so you can take it out of the integration. Yes, this you have seen. Yeah, v is equal to u plus at. U is the initial velocity, a is the acceleration. This kinematics, high school physics. So it's the same thing. But I want to know, so this is for one electron, and this is until there is no scattering event. Say electron started with v naught just after the scattering event. So just after a scattering event, its velocity is v naught, and v naught is, by the way, random. After the scattering event, where will the electron be? I don't know. It can be in any direction, it can have any velocity. after the scattering event, just after the scattering event. Now between two scattering events, this relationship is valid. Okay, as long as electron is not encountering any scattering, this is valid. So it started with V naught, accelerated a bit, and then again got scattered. Okay, the final velocity just before it scattered is V, and the time it took between the two scattering events is T. Okay, now this is the picture for one electron. What if I average this thing over all the electrons? So let's take the average. Average it out. So average I'm denoting by these brackets, angled brackets. So average of this velocity. Okay, this is the velocity just before the next scattering event. This is the initial velocity just after one scattering event. Minus of electric field is constant, mass is constant. So where will the average go? Over time. Because time between two scattering events for different electrons can be different. Even for the same electron, it can be different over multiple scattering events. True. So this thing is called drift velocity, average velocity. Okay. This thing is going to be 0. If you take a random velocity and average it out over an ensemble of electrons, what will be the value? 0, because it is random. And what is this tau average? This T average, it becomes tau. And tau is called mean scattering time. Average time between two successive scattering events. Average time between two successive collisions, you can also say. Okay, so that is your scattering time, or mean scattering time, or you can also say relaxation time. This is usually denoted by Vd. D means drift. So this is the velocity that is very important for us. Average velocity, not the actual velocity. Actual velocity is only possible when you remove all the scattering. Okay, when we talk about something like ballistic transport. So ballistic transport is going like a ballistic missile. Okay, it is not encountering any scattering. Then yes, the theory that we talked about, that is kind of valid only in special circumstances. In most of the cases, if you have a long semiconductor bar, even if you have say some transistor of channel length say 50 nanometer, 100 nanometer, it is going to encounter a lot of scattering events. Okay, but what if my transistor has a very small channel length? It can happen that an electron which is going from source to drain, it goes without any scattering event. Well, that is ballistic. Okay, so we're not talking about that. We're talking about when it is averaged out. So the drift velocity. Okay, so what is the drift velocity? It comes out to be Vd is equals to, so this becomes tau, so minus q tau by m into the electric field. So V is equals to some constant times electric field, and this thing q tau by m, this is called mobility of electron. So mobility determines how easy it is for an electron or a hole to move in an electric field. Okay, I apply a certain electric field in different materials. Now, depending upon the material, an electron can gain a lot of drift velocity or a smaller drift velocity. Okay, the factor that determines it is, it's called mobility. And what does mobility depend on? Mobility depends on this tau and the effective mass. So if my electron is say heavy, it will be difficult for the electron to move. Yes, in a semi-classical picture. If there is a very frequent scattering, what will happen to tau? Will it decrease or increase? If there is a frequent scattering, tau will decrease or increase? Decrease. Frequent scattering means the time between two successive collisions, it's now reduced. So tau will decrease. What will that do to the mobility? It will reduce it. Okay. Heavier effective mass, smaller tau, both of them are detrimental to the mobility. Okay. So let me ask you a question now. If you have a crystal, say silicon crystal, okay, perfect crystal, versus say I have polycrystalline silicon. Silicon can also be in polycrystalline form. Which one is better for transport? Single crystal, correct? Polycrystalline silicon will have defects, a lot of scattering, grain boundaries, so that will reduce the mobility. Okay, more frequent scattering. Yes. If there is a drift velocity, there will be some current associated with it. Yeah, so your electron distribution in an electric field, it is drifting. If it is drifting, the charge is moving. Charge is moving, so there should be a current. For electron, current will be in the opposite direction of the movement of the electron. For holes, it will be in the direction of the movement of the holes. So now let's calculate that current. So say I have this silicon bar, and let me take a cross section of this here and another cross section just a dx distance apart. So it's a very small distance, and there are electrons, so there will be some electrons within this small volume. Yes, there will be some electron. See, I have applied the electric field here in this direction, so where will the electron drift? In the opposite direction. So drift velocity will be in this direction, although the current will still be in this direction because the electrons are moving like this, so current is in the direction of electric field. True. Now we need to calculate that drift velocity. Okay, sorry, the drift current. Now current is given by what? dq by dt, rate of flow of charge. So if I have time dt and I have a cross section, and through that cross section dq amount of charge has passed, then I say that dq by dt is the current through that cross section. Okay, so let's adopt the same definition and let's try to calculate the drift current. Okay, before that, say I have an electron here, okay, and in dt time this electron will cross this distance dx. It takes dt time for this last electron to cross this distance dx. But when it crosses this distance dx, all the electrons that were there in front of it have already crossed this distance dx. True? Okay, focus on this cross section. This is going to take dt time to just reach here. But in that dt time, all these electrons have already crossed it, because I am assuming that all of them are moving with the same drift velocity, same average drift velocity. So if this is crossing it in dt time, the electrons which were ahead of it, they have already crossed. So in dt time, all of this charge has already passed through this cross section. You get my point? Okay, so if I have to calculate the current through this cross section, what is the amount of charge that has passed through this cross section in dt time? The charge which is inside this volume. What is the charge inside this volume? If say my electron density at this particular x is n, what will be the charge inside this volume? Say area of cross section is A, what will be the charge? So free electron density, right? Number density into minus q, that gives you charge density. Now you need to multiply this charge density with the volume to get the total charge. What is the volume? Area times dx. Okay, minus q times n times a times dx is the amount of charge which is inside this small volume. So this is the charge, This is the dt. You divide the two. Dx by dt. You know dx by dt. What is dx by dt? Velocity. So that is the drift velocity. So it is minus q into n into vd into a. That's your drift velocity, drift current. What does it depend on? The carrier density, of course, and the drift velocity. So multiplication of the carrier density and the drift velocity, that determines my drift current. N denotes it's the electron current. So similarly, there can be hole current as well. So this is the total current, but you can also define current density. So current density is current per unit area. So if I divide it by the area, so that becomes the current density then. J and drift. So it is minus q into n into vd. Okay, and vd is minus of mu into zeta. True, mobility times the electric field. So you can also express the j in terms of the electric field and the mobility and the carrier density. What is this thing, by the way? Does it look familiar? J is proportional to electric field. J is equals to sigma E. Remember this thing. This is Ohm's law. Current density is equals to, this thing is called conductivity times electric field. So this thing that you see in the bracket, it is nothing but the conductivity. This thing. Okay, this is the conductivity only because of the electrons, because I'm only talking about the electron movement. There can be some conductivity contribution which is coming from the hole. The total conductivity will be the sum of the two. So the total drift current, as I said, there will be a drift current because of the holes, JP drift. So that is Q into P into mu P into zeta. And the total current is going to be, mu P is the hole mobility here. So electron mobility and hole mobility, they are different. And typically, hole mobility is smaller than the electron mobility. Okay. Why? What does the mobility depend on? What does it depend on? Scattering time and mass, effective mass. Typically, the hole effective mass is larger compared to the electron effective mass. Actually, the movement of hole is in the valence band. It is difficult for a hole to move around compared to an electron which is just free to move. Okay, for a hole movement, you actually have to break the bond. You have to create a vacancy. So if you look at the EK curvature, you will typically find that the magnitude of the hole mass is larger. Although there are ways to make them very similar. So in advanced transistors, they do these tricks. Actually, they modified the band structure. They will apply some strain or something, and that will change the curvature of the EK. And if you are changing the curvature of the EK, you are changing the effective mass. Okay. Why is it desirable to have similar electron and hole velocity, hole mobility, by the way? Why is it desirable? I mean, it is not, but do I want it? Yes, I want it, but why? What? Output efficiency. I mean, power, yes. I mean, why? Say, of course, if I have the mobility similar to electron, it is going to increase my current. True. Okay, so it will improve my performance. If I have a larger current, it will improve my speed of the transistor. Okay, that's one thing. Another thing is that if you remember this inverter characteristics, CMOS, digital inverter. So there you will see that you have this voltage transfer characteristic, and it really depends on, if you want a symmetric CMOS characteristic, it depends upon the mobilities of the transistors. Okay, the p-type transistor and the n-type transistor. Okay, so if their mobilities are not say equal, so you want a symmetric VTC, usually voltage transfer characteristic. If you don't have say symmetric, then you will have to find some other ways to make it symmetric. So what happens say in older technologies, bulk CMOS, so they will have an n-type transistor, one transistor, but they will have two p-type transistors, or the width will be twice just to compensate the effect of the mobility. Okay, width of the transistor actually determines the total current that can pass through the transistor. So if you say mobility is say half roughly, and you double the width, so that kind of compensates that effect. But what's the downside? It's taking more area. You don't want that. Okay, you don't want that. Say if my transistors are say now completely symmetric, I only need 1 and 1, and I get perfect symmetric VTC. In advanced transistor technologies, they are almost similar. Okay. Okay, so total drift current will be JN drift plus JP drift, of course, and it's given by this. You put the formula of this here, put the formula of this here, okay, and you take the electric field out, and this thing becomes your total conductivity. So conductivity contribution from the electron is this, from the hole is this. This is the conductivity of the semiconductor. So mobility and the electron and hole density, they together determine the conductivity. Let's look at the mobility a little more closely. So we have the mobility expression as this, Q tau by m star. Now of course it depends upon EK curvature, scattering time. I've talked about it before, but there can be different types of scattering. So there can be different factors that can affect the mobility. We have talked about the M. Yes, EK curvature. Yes, for different materials, EK curvature will be different. You apply some strain on the material, you can change the EK curvature. You can do all of those things. But scattering time is also important. So what are the factors that affect this scattering? There can be several factors. There can be several types of scattering. So let's look at those scattering events one by one. So the main mechanisms are phonon scattering. So phonon scattering is the first one, and it is a scattering due to the thermal vibrations of the lattice. You have a thermal vibration in your crystal, and electron is going to get scattered. Why the name phonon? Because according to quantum mechanics, electron cannot exchange energy with the lattice arbitrarily. It will only exchange the energy with the lattice in the form of some energy packets which are called phonons. You know the photon, right? Photon is what? The particle version of the light. Yes, it has an energy of h times the frequency, Planck's constant times the frequency, or h bar omega. Omega is say angular frequency. True. Or hc by lambda. Lambda is your wavelength, c is your velocity of light. A similar concept you can have for lattice waves. So there you have light waves, electromagnetic waves. Here you have mechanical waves going into the crystal. But according to quantum mechanics, I'll talk about it. Energy exchange can only happen in the discrete energy packets. So that discrete energy packet is called phonon, hence the name phonon scattering. Okay, so it can only exchange h bar omega form of energy with the lattice. Okay, omega is the frequency of the phonon. Okay, we'll talk about it in a little more detail. So this is the first type of scattering. So whenever the electron is say giving up its energy to the lattice, so it is emitting the phonons, right? It is emitting the phonon, it means it is giving up the energy. And where is that energy going? It's going to the lattice. What will happen to the lattice? It will heat up. opposite can also be true. Electron can also gain some energy from the lattice. It can absorb a phonon and becomes more excited. Its thermal energy, its thermal velocity will then increase. Okay, that's what precisely happens when you increase the temperature. Okay, it absorbs the phonons and increases, its energy increases. So absorption, emission, both can happen. There will be certain conditions in which one of them will be dominating. Second type of scattering can be Coulombic scattering. So this was because of the temperature vibrations. Coulombic scattering is because of the Coulombic force of any fixed charge that you have kept inside your semiconductor. Now what can be that fixed charge? That can be some ionized dopant atom. That can be some deep level center, some trap. That can be some interface charge. Interface charge means, say you have a MOSFET, you have some oxide, you have some channel, silicon. So at the interface of, say, oxide and the silicon, there can be some interface charges, because you are going from one material to the other material. The transition may not be perfectly smooth. You are changing the stoichiometry, one material to other material transition. So there can be a lattice mismatch. So this has some lattice constant, this has some lattice constant. Because of the lattice mismatch, there can be some defects, traps, and these traps will then capture the electron or the hole, and then they become charged. When they become charged, they will then try to scatter the electron, because whenever an electron is, say, going close to a negative charge, what will happen to it? It will scatter, right? So say this is the electron. So I throw an electron, what will happen to this? Its trajectory will be something like this. What if it is positively charged? It will still scatter. It's not that an electron is going to just go down in the positive charge. No. If it has some speed, it will be something like this. Say if I have an electron which is moving close by, so then it will try to attract it, so its trajectory can be something like this. Both of them are getting scattered. Yes, its k vector was in this direction, now it is k dash. So this is the Coulombic scattering. Third type of scattering is scattering by defects. I mean, that's kind of okay. So defect, say I have an atom absent from, say, its position, so then that is like a deformation, right? So imperfection in the lattice, so that will create the scattering event. You will be away from the perfect periodic potential then, right? Okay, so for example, in the polycrystalline materials, so there will be a lot of defects. So polycrystalline means you have different grains, and at the grain boundary of the two grains, there can be a lot of defects. So that will scatter. Okay, so regarding the mobility, so mobility is actually temperature and doping dependent. Of course, it should be. Yes or no? Should it be temperature and doping dependent? Doping dependent, it's very obvious, right? You are basically changing the charges that you put in your semiconductor. So that is going to cause the Coulombic scattering. What about the temperature? Of course, phonon scattering. Yes. So both of them affect the mobility. How does it affect? So typically, this is the plot that you get. Mobility, if you plot it as a function of the temperature, so you see that initially, the mobility increases. At the low temperature, it reaches a maximum value, then it starts to decrease. And the slope is temperature to the power something. It may not be exactly minus 3/2 as it's a very first order model that predicts 3/2, but it can be some power of temperature. It's called temperature power law sometimes. So why this behavior? So let's start with the high temperature first. If I am in this high temperature regime, of course, if I am increasing the temperature, mobility has to go down. There will be more and more energy exchange with the lattice, more and more phonon scattering. Okay. Now say I'm coming back, I'm reducing the temperature. Okay, mobility is increasing, but then it again starts to go down. Why this thing happens? Actually, at high temperature, this Coulombic scattering is not that much effective because my electrons have large thermal velocity. So if I have an electron which has a large thermal velocity, is it going to affect it? It has a large velocity, it can just pass by. Maybe a little bit deflection can be there, but if it has a large velocity, large speed, it can just pass by. Doesn't matter. So at high temperatures, this Coulombic scattering becomes ineffective. But if I reduce my temperature, you are basically bringing the velocities of the electrons down. So electrons will now have more time to interact with this guy. Yes? And this then strongly deflects it. So this will be like this. Interaction between the charges and the electron or the hole, it will increase when you reduce the temperature. So that's why, because of the more Coulombic scattering, it will again start to go down. Okay. If I show you some numbers, so they are like this. So if you plot the mobility, so here they have given the mobility of holes and electrons. So upper curve is for the electrons, lower curve is for the hole, and this is for silicon at 300 Kelvin, and it's the variation of the hole or electron mobility as a function of the doping. So this is the doping on the x-axis, net doping. Net doping, not the difference but the addition. Okay, because even if it is positive charge or negative charge, both are going to scatter. So Na plus Nd is the x-axis. Okay, Na plus Nd. So the total doping. So as you can see, when I have very small doping, mobility is almost constant, Coulombic scattering is absent, temperature is constant, so you are not increasing or decreasing the phonon scattering, it's just there. So it's constant, but as you keep increasing the doping, mobility is dropping. And look at these numbers. So these numbers at least you should remember for the silicon. So silicon, typically n-type mobility will be 1350 to 1400 centimeter square per volt second. That's the unit. So we specify the mobility in centimeter square per volt second. Okay. For the holes, it is smaller, around I think 500 or so. But 10 to the power 14 is a very small doping. So it's almost intrinsic. 10 to the power 14, if you have the doping, it's almost intrinsic. So do we really have 1400 mobility for the electron in real devices? Typically no, because you will always have some kind of doping, at least 10 to the power 16, sometimes 17, sometimes 18. So you will be somewhere here. So real doping levels will be around, for the electrons it will be 500, for the holes it will be 300. Those are the numbers. And this is the mobility in the bulk semiconductor. Okay. If I have a transistor, I can have some other effects. If we have time, we will talk about it, which can further degrade the mobility. So actual mobility for electron will be even smaller. It will be around 300. For holes, it will be around 100. Okay. So all of these things are very important for the performance of the devices. Now the mobility can be there for different scattering events. You know that. So if I have different types of scattering, how do I determine the mobility? You can have phonon scattering, you can have Coulombic scattering, other types of scattering. How do I calculate the mobility if I have several of these scattering events present simultaneously? So there is a rule called Mathiessen's rule that you can apply, and they can give you the individual contribution of different scattering events and different of scattering the mobility. So say you have a carrier, okay, and you know that mean scattering time because of any scattering event, it can be phonon scattering or Coulombic scattering or whatever. Say the mean scattering time is tau. Now what is the probability that an electron will suffer a scattering event in time dt? So that will obviously be dt divided by tau. Okay, tau is the average time between two successive collisions because of a particular event, because of a particular type of scattering, and dt is the time. In the dt time, the probability that a given electron will get scattered is dt by tau. True? If I give this electron more time, the chances are more that it will definitely get scattered. So dt by tau is roughly a good estimation of the probability. Now in the same time, of course, the electron can get scattered because of different types of scattering. Yes? So that increases the probability of an electron to get scattered. Say the probability because of phonon scattering is dt by tau 1. Because of Coulombic scattering it is dt by tau 2. Yes. What will be the total probability that it will get scattered in time dt? It will be the sum of the two. I am assuming that phonon scattering, Coulombic scattering or any other type of scattering that I will talk about, they are all independent of each other. They are not influencing each other. That's why I can simply sum up their probabilities to get the total probability. True. So basically the total probability will be dt by tau phonon plus dt by tau Coulombic plus dt by tau defect plus any other thing. Yes, and if I want to calculate, say, effective mean scattering time, how do I calculate that? I will equate it to some dt by tau, where tau is the effective mean scattering time. Okay, there can be different taus, but this tau is the effective one. It's the combination of all the other. And these all dt's will get cancelled. So what do you get? 1 by tau is equals to 1 by tau phonon, 1 by tau Coulombic, and so on. And I know that mu is equals to q tau by m. So q is proportional to tau, and q and m are constant. For one particular type of particle it is constant. Yes? So if tau follows this thing, mu will also follow this thing. You can simply put this formula here. This q and m star will get cancelled on the left and right hand side, and what you get is 1 by mu is equals to 1 by mu 1 plus 1 by mu 2 plus 1 by mu 3 and so on. This is called Matthiessen's rule. Okay? So mobilities add, but they add as 1 by mu 1 plus 1 by mu 2 and so on. Now let's look at this m star a little more closely. So we have seen that, okay, we have seen normal rest mass. Of course, you know what is normal rest mass. Then we talked about effective mass. Now effective mass is the curvature of Ek, and curvature can be different in different directions. So for example, in silicon I have ellipsoidal constant energy surface, so I can have longitudinal effective mass, transverse effective mass. And then we calculated the density of states effective mass. What was the density of state effective mass? Okay, I can calculate the density of states by using different electric different effective masses in different directions, right? So I can have, for the ellipse we saw all of that derivation, but density of state effective mass gives me a mass. What if I replace this whole 6 valleys of the silicon with one sphere, a spherical constant energy surface, and just use one single mass, right? So then that mass was my density of state effective mass. So that was just to describe the density of states. If I put the same mass, say, here, that will be wrong, because that was just for the calculation of density of states. So it's the mass which will give you the same density of states if you have an actual silicon with 6 ellipsoids. Okay. Here I will have to use some other effective mass. That will not be density of state effective mass, that is called conductivity effective mass. So whenever I am talking about the transport, I don't use density of state effective mass. I use conductivity effective mass. How do we calculate that? It's a little different it's actually very different from the calculation of our density of state effective mass. How do I calculate it? Okay, let's see. Okay, now effective mass in the formulas such as say velocity or the mobility will be the conductivity effective mass. And let me assume a silicon sample, bulk silicon. So I know all of these values, ellipsoid. Yes. 6 ellipsoids I have for silicon. And let me assume that I consider the electron conduction along any of these valleys, say this or this. Say, let me assume that I apply some electric field along 0, 1, 0 direction, and I start to see what is the behavior of these electrons in terms of transport. How do they behave? Okay. Now, all of these, the center of all of these valleys, right? That is like the conduction band H. You know that, right? The center point, the center K, there will be a center K here, right? It's in the reciprocal space, you know that. So reciprocal space means it will give you some K value. So K at the center of this, that corresponding to that K, the energy will be the band H. And you know that most of the electrons are concentrated near those valleys. So a lot of electrons will be there. And because they are all equivalent, so all of them will have the same number of electrons, all of the 6. True. So if I apply an electric field, all the 6 matter because all of them have equal concentration of electrons and all of them are near the conduction band edge. So most of the electrons are staying here. Yes, electrons can also be there in some other direction, but majority of the electrons are in these valleys. If I apply an electric field in this direction, electron will start to move. Now look at an electron which is there in this ellipsoid. Because my electric field is in this direction, right, and electron will also move electron will move in the opposite direction of the electric field. So basically if this is 0, 1, 0 electric field is here, so electron will start to move in this direction. What is the mass, what is the effective mass with which it is moving? What is the effective mass with which it is moving now? It is going along the longitudinal direction. So which effective mass is going to be important here? You remember this? So there is a longitudinal effective mass, then a transverse effective mass, then a transverse effective mass. If my electron is moving along a particular special direction, so I will have to use the effective mass in that direction. Do you agree? Yes? So in this case, that direction is longitudinal direction. So I will use ML star. For which values I will use ML star? For this valley as well as this valley. So valley number 1 and 2. For both of them I will use ML star. Correct? So when I apply my Newton's law, dV by dt is equals to minus of Q electric field. So this M is going to be ML star. Yes? And V is the longitudinal this velocity. Okay. Now let's look at the other values. So 3, 6, 5, 4, all of them are equivalent as far as the transport is concerned. So let me just look at, say, at 3. Electric field is in this direction. Electron is going to move in this direction. Yes? Now which effective mass will you use? for this electron, if it is moving like this, which effective mass will you use? Basically, you have tilted it like this, yes? Yeah? So this is definitely not along the longitudinal direction, it is exactly perpendicular to that. So exactly perpendicular to that, which effective mass is there? Transverse effective mass. So for this, and also this and this, they will also be transverse. Yes? I mean, electric field is here, so this will also be transverse. So for all four of them, you will use the transverse effective mass. Okay? So this equation is after you apply this Newton's law and integrate. So for longitudinal, I get this. For transverse, I get this. You can now take the average. Yes, so this is going to become 0. This is going to become 0. This t is going to become, this scattering time. Yes, tau. So now what if I say that, okay, I don't want to use, two formulas. So I don't want to count every value. Give me one formula, and I just want to use, this q tau by m star into electric field, and give me just one formula. I don't want, every direction I'm calculating it. So basically I want something equivalent. I want to replace this thing with one velocity expression, which is q tau by m, and m is called conductivity effective mass, okay, times the electric field. So how do I calculate that? Basically what I will do, the simplest way would be, let me just take the average. So some of them are moving with this effective mass, some of them are moving with the transverse effective mass. Let me just take the average. Okay, so how do I take it, the average? So I have this velocity, average velocity. So let me average it over 6 valleys. So the weight factor will be 2 valleys have ml star, 4 valleys have mt star. I just simply add all of those velocity divided by 6, and that gives me some kind of average. Okay, and this is what it gives me. And what is the equivalent velocity? I told you I just want to use one formula. So that formula is this, q tau by mnc star. Nc means the conductivity effective mass of n-type electron, n-type, so n stands for electron, times the electric field. So what will be my m star nc? That will be this thing. Okay, this thing. So this becomes the harmonic mean of mx star, my star, and mc star. Yes, how do you take harmonic mean? So you have the total number divided by, say you have x1, x2, x3, x4. So harmonic mean will be what? 4 divided by 1 by x1 plus 1 by x2 plus 1 by x3 and so on. True. So harmonic mean of mx star, my star, mg star, what will be that? So one of them is ml and 2 of them is mt. Yes. So 3 divided by 1 by ml star plus 1 by mt star plus 1 by mt star, which makes it 2 by mt star. So this is the harmonic mean. In the density of state effective mass, it was geometric mean. Remember? Conductivity effective mass, harmonic mean.